Hello, in this lecture we'll find out the length of chord CB. In the drawing we have a semicircle. We know that the center of this semicircle is at this point, point O. Inside the semicircle we have square DEFO, this square, and we know that the area of this square is 5 units. And our mission is to find out the length of this chord called CB. So first of all, because DEFO is a square, we know that all the angles inside the square are right angles. That is to say, those 4 angles, they are all right angles. So when I write it down, this angle equals to 90 degrees. This angle is also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle it is also equals to 90 degrees. And we also know that the area of this square, DEFO, is equals to 5 square units. So I can write down that the area of square DEFO is equal to 5 square units. And we actually know that if this is a square, and one side of this square is equal to x, so all the other sides also equals to x. So the area of this square, is equal to x squared. Okay. So here we copy our square in this page and we use the formula in order to find out the length of one side. So this is square DEFO, the copies from the original drawing. We know that the area of this square is equal to 5 square units. All the other sides of the square, we define the length of one side as x, so for all the other sides are equal to x. So according to this formula, the area of this square is x squared. The area of square DEFO, our square, is equal to x squared. But it is given us in the question that the area of square DEFO is equal to 5 square units, so we can substitute the area by 5, so 5 equals to x squared. We will take a root out of this equation, and here we get that x equals to the square root of 5 units. So we found out that one side of this square DEFO, equals to the square root of 5 units. That is to say, all the sides are equal to the square root of 5 units. Here we can write down that the length of DE is square root of 5 units, EO equals to the square root of 5 units, FO equals to the square root of 5 units, and finally DF, it is also equals to the square root of 5 units. In the next step, we join points O and D together by a straight line. By joining points D and O, we have created here the right triangle DFO. the right green triangle, triangle DFO. So I will copy the right green triangle in the new page and we will implement the Pythagoras theorem on this right green triangle DFO. So this is the right green triangle DFO that I copied from the original drawing. We know that DF equals to FO equals to the square root of 5 units. They are both the sides of the square. So we will implement the Pythagoras theorem in order to find out the value of the hypotenuse DO. So here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DO, therefore the square of the hypotenuse is DO square. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DF square plus FO square. Okay. So DO square, that is the square of the hypotenuse of the right triangle DFO, must be equal to DF square. DF equals to the square root of 5, therefore DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5, therefore FO square equals to square root of 5 square. So we found out that DO square equals to the square root of 5 square is 5, plus square root of 5 square is 5. In conclusion, we found out that DO square equals to 5 plus 5 is 10. Here we'll take a root out of this equation and we'll get that DO equals to the square root of 10 units. That is to say, the length of the hypotenuse DO it is equal to square root of 10 units. So we can write down here that DO equals to the square root of 10 units. What is the other definition of DO? Line segment DO starts from the center of the semicircle and ends at point D, that is a point on the semicircle itself. This is exactly the definition of a radius. So DO is the radius of the semicircle and we know that is equal to the square root of 10 units. That is to say, the radius of this semicircle equals to the square root of 10 units. What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the semicircle, and ends at point B, that is a point on the semicircle itself. This is exactly the definition of a radius. That is to say, OB is the radius of the semicircle that is equal to the square root of 10 units. Likewise, if we focus on line segment OA, it starts from the center of the semicircle, that is to say from point O, and that's at point A, that is the point on the semicircle itself. This is exactly the definition of a radius, that is to say OA is the radius of the semicircle that is equal to the square root of 10 units. In the next step we will focus, in the next step I will present to you a new rule and we implement the new rule in our drawing. Okay. According to the new rule, that is actually rule number 1. The sum of the angles on one side of a straight line, is equal to 180 degrees. I will explain what is the meaning of this rule. So actually, if we have a straight line here, AB, it is a straight line. You can choose any point on this straight line AB. For example, we choose this point, we define this point as point K, and here it will be side KL, and according to this rule number 1, the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on the upper side of the straight line AB, this is to say on this side, at point K, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point K? We have this angle, that is actually angle AKL, plus this angle, this is actually angle LKB. In total, the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. The same thing is true in relation to the lower side of the straight line. This is the lower side of the straight line AB. If you focus on the lower side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. That is to say, this angle must be also equal to 180 degrees. So we actually can implement rule number 1 in our drawing. Why? Because in our drawing we have this semicircle, and in any semicircle, AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So actually, if we focus on the upper side of the straight line AB, here at point O, here the sum of the angles must be equal to 180 degrees according to this rule number 1. So which angles we have at the upper side of AB here at point O? We have this angle, that is a right angle, it is equal to 90 degrees, plus the missing angle, this angle is the missing angle, this is actually angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. I'll repeat again, at the upper side of AB at point O, the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus angle EOB must be equal to 180 degrees. Here we will subtract 90 degrees from this equation, and we will get that the missing angle EOB equals to 180 degrees minus 90 degrees, it is 90 degrees. Here angle EOB equals to 90 degrees. The missing angle EOB, this is angle EOB, that is equal to 90 degrees, it is a right angle. Okay. And because of the fact that angle EOB is a right angle, therefore triangle EOB, this triangle is a right triangle. Here, the pink triangle is a right triangle. Therefore, we can implement the Pythagoras theorem on the pink right triangle EOB. So we copy the right pink triangle EOB in a new page, and we'll implement on it the Pythagoras theorem. Okay. So actually, this is the right pin triangle EOB that I copied from the original drawing. So here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here EB is the hypotenuse, therefore the square of the hypotenuse is EB square. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO square plus OB square. Okay, according to the Pythagoras theorem, in the right triangle EOB, we'll get that EB square equals to EO square plus OB square. So EB square equals to EO square. EO equals to the square root of 5, therefore EO square equals to the square root of 5 square plus OB square. OB equals to the square root of 10, therefore OB square equals to the square root of 10 square. So in conclusion, we found out that EB square equals to the square root of 5 square plus square root of 10 square. So EB square that is the square of the hypotenuse equals to the square root of 5 square. The square root of 5 square, it is also, of course, equals to 5 plus the square root of 10 square. The square root of 10 square equals to 10. So in conclusion, we found out that EB square equals to 5 plus 10, that is 15. Here we take out of this equation and we get that EB equals to the square root of 15 units. Here the hypotenuse EB equals to the square root of 15 units. Okay. And segment EB equals to the square root of 15 units. So our mission is to find out the length of chord CB. We already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we will do a construction. We will complete this semicircle to a circle. Okay. This is the first step that we have to do. So we actually completed this semicircle to a circle. In the next step, we'll extend line segment OE on both sides, in the upper side and also in the lower side. So here we will extend OE towards the upper side of the circle by a straight line until it touches the circle. And we define the touching point of the extended OE in the circle as point M. In the next step, we will extend line segment EO towards the lower side of the circle until it touches the circle, and we will define the touching point of the extended EO in the circle as point N. So what is the definition of line segment ON? Line segment ON starts from the center of the circle, that is to say from point O, and ends at point N, that is the point on the circle itself. This is exactly the definition of a radius, that is to say ON is the radius of the circle, that is equal to the square root of 10 units. And what is the length of EN? From the drawing it is very easy to see that EN equals to, here EN equals to EO plus ON. So write it down. EN equals to EO plus ON. EN equals to EO, that is square root of 5, plus ON, that is square root of 10. In conclusion, we found out that EN equals to the square root of 10 plus square root of 5. can write down here that En equals to the square root of 10 plus square root of 5. Likewise, point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to the square root of 10 units. We know that EO equals to the square root of 5 units. And what is the length of line segment ME? It is very easy to see from the drawing that ME equals to MO minus EO. Again, ME equals to MO minus EO. ME equals to MO minus EO. So ME equals to MO, that is square root of 10, minus EO, that is square root of 5. So in conclusion, we found out that ME equals to the square root of 10 minus square root of 5. We already found out that ON equals to the square root of 10 and EB equals to the square root of 15. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. According to the new rule, that will be actually rule number 2. Rule number 2 is true in any circle, so I write down that in any circle, if chord AB intersects with chord CD, its point O. So here I will draw a circle that could be any circle. So this is chord AB. It intersects with chord CD. This is called CD. In the intersection point occurs at this point. The intersection point is defined as point O. Okay. So according to rule number 2, we'll get that the following equation is true. That AO times OB equals to CO times OD. I repeat again, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. AO times OB equals to CO times OD. So whenever two chords intersect with each other in a circle, we can implement this rule number 2. So we can implement rule number 2 in our drawing. Why? Because in our drawing, we have chord MN, this is called MN, that intersects with this chord called CB at point E. So I copy the two chords that intersect with each other in a new drawing and we'll implement rule number 2 in our drawing. Okay. You can see that chord MN passes through the center of the circle. So this is called MN. That intersects with this chord called CB. Intersects with chord CB. The intersection point occurs at point E. So I write it down in our original drawing. Chord MN intersects with chord CB, the intersection point occurs at point E. Therefore, according to rule number 2, we get that ME times EN, equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5. And EB equals to the square root of 15. So here we can substitute ME by square root of 10 minus square root of 5. We can substitute EN by square root of 10 plus square root of 5, and we can substitute EB by square root of 15. C is the missing line segment, and EB equals to the square root of 15. Here we have the algebraic identity that A times B equals to B times A, therefore we can change the order here. Instead of square root of 10 or square root of 5, in the first place we will put square root of 10 or plus square root of 5 in the first place. And then in the second place we will put square root of 10 and square root of 5 according to the rule that A times B equals to B times A, and it is equal to CE times square root of 15. Okay. So here we have the algebraic identity that states that A times B times A plus B times A minus B equals to A square minus B square. We will use this trigonometric identity in order to find out the value of this expression. In our specific expression, the value of A is equal to the square root of 10 units. The value of B, it is equal to the square root of 5 units. And A plus B times A minus b equals to a square minus b square. That is to say, according to this algebraic identity, this expression equals to a square minus b square. Okay? So we can substitute this expression by a square minus b square. If a equals to the square root of 10, then a square equals to 10, of course, minus b square. If b equals to the square root of 5, then b square equals to 5, of course. So in conclusion, we found out that a square minus b square equals to this expression that is equal to a square minus b square equals to 10 minus 5. And this expression equals to CE times square root of 15. This equals to CE times square root of 15. 10 minus 5 is 5, so 5 equals to CE times square root of 15. Here we will divide this expression by square root of 15, and we get that CE equals to 5 over square root of 15. Okay. So CE equals to 5 over square root of 15. And we also found out that the missing line segment CE equals to 5 over square root of 15. And what is the value of chord CB, the chord that we are looking for? Chord CB, it is equal to CE plus EB. Again, CB equals to CE plus EB. CB equals to CE plus EB. Again, the chord that we are looking for is called CB, and it is equal to CE plus EB. We just right now found out that CE equals to 5 over square root of 15, and we already found out that EB equals to the square root of 15. So the answer to the question is that the length of chord CB, the chord that we are looking for, the length of this chord equals to 5 over square root of 15 plus square root of 15. Here we will simplify this expression because we don't want a square root in the denominator. So we'll multiply square root of 15 by square root of 15, and then we will divide it by square root of 15. That is to say, we multiply it by 1, therefore we will change nothing in this number. In this way, we will have a common factor with this expression. So CB equals to 5 over square root of 15, and then we will multiply square root of 15 by square root of 15, and then we will divide it by square root of 15. Okay, so here CB equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. So we found out actually that the length of the chord that we are looking for, CB, is equal to 5 plus 15 is 20. We have 20 the numerator over square root of 15. Here we will multiply this expression by square root of 15, and then we will divide it by square root of 15 in order to eliminate the square root in the denominator. So CB equals to 20 over square root of 15. This is the expression. We will multiply this number or expression by square root of 15, and then we will divide it by square root of 15. So we multiply it by 1, so we change nothing. Therefore it is allowable. So we get that CB equals to 20 times square root of 15 over square root of 15 times square root of 15 is 15. Here we will divide both the numerator and the denominator of this expression by 5, and we will get that CB equals to 20 over 5 is 4. So in total, in the numerator, we have 4 times square root of 15 over 15 over 5 is 3. So in conclusion, we found out that the length of this chord called CB, it is equal to either 5 times square root of 15 over 3 units, or in terms of numbers, it is equal to 5.164 units. Okay, so we finished with this question. In the next step, I'll summarize the lecture. I repeat again, the length of this chord called CB, it is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, the length of chord CB, it is equal to 5.164 units. Okay. In the original drawing we had actually a semicircle. This is the semicircle that we had. We know that the center of this semicircle is at this point O. We also know in this semicircle we have this square DEFO, and we know that the area of this square DEFO is equal to 5 square units. And our mission is to find out the length of this chord called CB. So because of the fact that DEFO is a square, we know that all the angles inside the square are right angles, so those 4 angles that are inside square DEFO, they are all right angles. That is to say, each of them is equal to 90 degrees. Okay. We know that the area of square DEFO is equal to 5 units. The area of any square, so this square could be any square. The area, we know that all the sides of the square are equal to each other. So the area of this square is equal to x times x, that is x squared. Okay. So we will define one side of our square DEFO as x. The length of one side of square DEFO, according to our definition, will be equal to x. And according to this formula, the area of square DEFO equals to x squared. But we know that the area of square DEFO equals to 5 square units, so we can substitute the area by 5. And we get that 5 equals to x squared. We'll take a root out of this equation, and we'll get that x equals to the square root of 5 units. That is to say, each side of square DEFO is equal to square root of 5 units in its length. All the sides are equal to the square root of 5 units. Okay? In the next step, we will join points D and O together by a straight line. In this way, we created the green right triangle DOF. Why it is a right triangle? Because of the fact that this angle is equal to 90 degrees. Then I copied this right triangle DFO in a new page, and we implemented the Pythagoras theorem in this right green triangle DFO. This is the right triangle DFO that I copied from the original drawing. We know that DF equals to FO equals to the square root of 5 units. They are both sides are the sides of the square. And the only side that is missing is side DO, that is the hypotenuse of this right triangle DFO. So we can implement the Pythagoras theorem on this right triangle DFO in order to find out the length of the hypotenuse DO. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse in any right triangle equals to the sum of the squares of the perpendiculars. The hypotenuse is DO, therefore the square of the hypotenuse is DO squared. And it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to DF squared plus FO squared. So dO square equals to dF square. dF equals to the square root of 5, therefore dF square equals to the square root of 5 square. Plus FO square. FO equals also to the square root of 5, therefore FO square equals to the square root of 5 square. In conclusion, we found out that dO square equals to the square root of 5, that is 5, plus square root of 5, the square root of 5 squared, that is 5, plus square root of 5 squared, that is also 5. So dO square equals to 5 plus 5, that is 10. We took a root out of this equation and we found out that dO equals to the square root of 10 units. So the length of the hypotenuse dO equals to the square root of 10 units. Okay. But dO, it is not only the hypotenuse of this right again triangle DFO, but it is also the radius of this semicircle. Why? Because of the fact that point O is the center of the semicircle and point D is the point on the semicircle itself. This is exactly the definition of a radius. That is to say, DO is the radius of the semicircle that is equal to the square root of 10 units. So the radius of this semicircle equals to the square root of 10 units. Here O is the center of the circle, B is the point on the circle itself, therefore OB is the radius of the circle that is equal to the square root of 10 units. Likewise, if we focus on the line segment OA, point O is the center of the semicircle, point A is the point on the semicircle itself, therefore OA is the radius of the semicircle that is equal to the square root of 10 units. Then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we have this straight line AB, we choose any point on the straight line AB, for example this point K, and this is side KL. According to this rule, rule number 1, the sum of the angles on one side of this straight line is equal to 180 degrees. So if we focus on the upper side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB? This is the upper side and this is the lower side of the AB. In the upper side of AB at point K, we have this angle that is actually angle AKL plus this angle that is actually LKB. In total, the sum of those two angles, that is to say angle AKL plus angle LKB, must be equal to 180 degrees according to this rule, rule number 1. Likewise, if you focus on the lower side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. That is to say, this angle, it is also equal to 180 degrees. We can implement rule number 1 in our drawing. Why? Because in our drawing, we know that this is a semicircle according to what was given us the question. AB, it will be always the diameter of the semicircle. So AB is the diameter of the semicircle, it is absolutely a straight line. So if we focus on the upper side of the straight line AB here at point O, here the sum of the angles must be equal 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees, plus this angle, the missing angle is angle EOB. In total, they must be equal to 180 degrees according to rule number 1. Okay? So again, if we focus on the upper side of the straight line AB at point O, according to rule number 1, the sum of the angles must be equal to 180 degrees. Which angles we have at the upper side of AB at point O? We have one angle that is equal to 90 degrees plus the missing angle that is angle EOB. In total, they must be equal to 180 degrees according to rule number 1. Here we subtracted 90 degrees from this equation and we found out that the missing angle EOB equals to 90 degrees. So this angle is the right angle, it is equal to 90 degrees. So if angle EOB is the right angle, it means that the pink triangle EOB is the right triangle. So we can implement the Pythagoras theorem on the pink right triangle EOB. So I copied the pink right triangle here and we implemented the Pythagoras theorem on this triangle. Here we've already found out that EO equals to the square root of 5 units. OB is the radius of the semicircle that is equal to the square root of 10 units. The only missing, this angle equals to 90 degrees according to rule number 1. The only missing side is the hypotenuse EB. According to the Pythagoras theorem on this right triangle EOB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO square plus OB square. Okay? So EB square equals to EO square plus OB square. EO equals to the square root of 5. Therefore, EO square equals to the square root of 5 square. So EB square equals to the square root of 5 square plus BO square. BO equals to the square root of 10. Therefore, BO square equals to the square root of 10 square. Therefore, in conclusion, we found out that EB square equals to the square root of 5 square plus square root of 10 square. That is to say, EB square equals to the square root of 5 square is of course 5, and the square root of 10 square is 10. So in conclusion, we found out that EB square equals to 5 plus 10, that is 15. Here we took out of this equation and found out that EB equals to the square root of 15 units. Here the hypotenuse EB equals to the square root of 15 units. And here also we can write down that 970 EB equals to the square root of 15 units. We are looking for the length of chord CB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of chord CB is to find out the length of line segment CE. This line segment CE, in order to find out the length of line segment CE, we did the construction. We completed this semicircle to a circle, and then we extended line segment EO on both sides, on the upper side and in the lower side. On the upper side we extended OE by a straight line until it touches the circle at point M. Then we extended EO towards the lower side of the circle until it touches the circle at point N. Here, what is ON? O is the center of the circle, N is the point on the circle itself, therefore ON is the radius of the circle that is equal to the square root of 10 units. What is the length of line segment EN? From the drawing it is very easy to see that EN equals to EO plus ON. EN equals to EO plus ON. That is to say, EN equals to EO that is square root of 5 plus ON that is square root of 10. So in conclusion, we found out that EN equals to the square root of 10 plus square root of 5. Likewise, OM is the radius of the circle because of the fact that point O is in the center of the circle, and point M is the point of the circle itself. Therefore, OM is the radius of the circle that is equal to square root of 10 units. We've already found out that OE equals to EO equals to the square root of 5 units. And what is the value of ME? The value of line segment ME, it is equal to OM minus EO. Again, ME equals to MO minus EO. Again, ME equals to MO minus EO. So ME equals to MO, that is square root of 10 units, minus EO, that is square root of 5 units. So in conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. We have already found out that ON equals to the square root of 10 units and EB equals to the square root of 15 units. So in the next step, actually presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, that is actually rule number 2, that is true in any circle. So in any circle, if we have chord AB, this is chord AB, that intersects with chord CD, this is chord CD, and the intersection point occurs at point O. So if this is the situation, then according to this rule number 2, CO times OD equals to AO times OBO. AO times OB equals to CO times OD. We actually can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN, this is chord MN that intersects with chord CB, this is chord CB at point E. The intersection point of the two chords is at point E. Therefore we can implement rule number 2. So I copied the two chords that intersect with each other in a new page and implemented rule number 2 in our drawing. Again, here we have chord MN that intersects with chord CB at point E. Point E is the intersection point between the two chords. Again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5, and EB equals to the square root of 15. CE is the missing line segment. So we substituted ME by square root of 10 minus square root of 5. We substituted EN by square root of 10 plus square root of 5. CE is the missing line segment, so we left it as it is. And finally EB equals to the square root of 15, so we substituted EB by square root of 15. And we got this equation, square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. According to the algebraic rule that A times B equals to B times A, we can substitute the order of the two expressions instead of writing the first expression, that is minus square root of 10 and square root of 10 minus square root of 5, we can write in the first place square root of 10 plus square root of 5 times square root of 10 minus square root of 5. That is equal to CE times square root of 15 according to rule number 2. Okay. Then this expression, we can find out the value of this expression according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to the square root of 10 units and B equals to the square root of 5 units. Here you can see that A equals to the square root of 10 units and B equals to the square root of 5 units. And this expression, it is equal to A squared minus B squared. According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. But what is A squared minus B squared according to the algebraic identity? According to a specific expression, if A equals to the square root of 10, then A squared equals to 10, and if B equals to the square root of 5, then B squared equals to 5. So A squared minus B squared is 10 minus 5. So in conclusion, we found out that the value of this expression is equals to 10 minus 5. According to the algebraic identity, that A plus B times A minus B equals to A squared minus B squared. Okay. So A squared minus B squared, that is actually 10 minus 5, equals to CE times square root of 15, according to rule number 2. 10 minus 5 is 5. So in conclusion, we found out that 5 equals to CE times square root of 15. Here we divided this equation by square root of 15 and we found out that CE equals to 5 over square root of 15. Here we found out that CE equals to 5 over square root of 15, and what is the value of the chord that we are looking for, CB? From the drawing it is very easy to see that CE equals CB, here CB, this chord, equals to CE plus EB. Again, CB equals to CE plus EB. So CB equals to CE, we have already found out that CE equals to 5 over square root of 15 and EB equals to square root of 15. So in conclusion, the answer to our question is that the length of this chord CB is equal to 5 over square root of 15 plus square root of 15. Here we simplified this expression because we don't want square root in the denominator. Therefore we multiply square root of 15 by square root of 15 and then we divide it by square root of 15. So we multiply by 1, therefore we change nothing. In this way we actually have square root of 15, we'll have a common factor with this 5 over square root of 15. Again, so CB equals to 5 over square root of 15, then we multiply square root of 15 by square root of 15, and then we divide it by square root of 15. So in conclusion, we found out that CB equals to 5 plus square root of 15 times square root of 15 is 15. So in the numerator we have in total 5 plus 15, in the denominator we have square root of 15. 5 plus 15 is 20, so in the numerator we have 20, in the denominator we have square root of 15. So in conclusion, we found out that CB equals to 20 over square root of 15. Then we multiply this expression by square root of 15, and then we divide it by square root of 15. So we multiply it by 1, so we change nothing. We did it in order to eliminate the square root in the denominator. So we got that CB equals to 20 times square root of 15, and the denominator we have square root of 15 times square root of 15, that is 15. Here we found out that CB equals to 20 times square root of 15 over 15. Here we divided both the numerator and the denominator by 5. So here 20 over 5 is 4. So in total the denominator we have 4 times square root of 15. In the denominator we have 15 over 5, that is 3. So in conclusion we found out that the length of this chord called CB, it is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, the length of this chord called CB, it is equal to 5.164 units. Okay, thank you very much.